Okay. So we're looking at ordinary differential equations. In the sense, these are just equations which will contain a variable or an unknown and the derivatives of that unknown. This is a differential equation, first order. The order will refer to the, for example, when the highest derivative is only the first derivative, then the order of this differential equation is 1. But if you have a differential equation where the highest derivative is, let's say, a power 2, like in this case, and then maybe you have plus 2, and then you can say dy, dx, you can say plus, let's say 4xy is equals to, can put 1, can put 0, doesn't matter. So here, the order of the derivative, so here the highest derivative, that's a 2 there. So this is also a differential equation. Now you have to be very careful. These two are different. This term here and this term here are different. The first term, which is this is the second derivative of y with respect to x. But this one, however, is just the first derivative being squared. So be able to distinguish between the square of a derivative and the second derivative. So again, it's all based on the placement of where that 2 is. So these are just some examples of differential equations. Now, differential equations will have solutions which are equations. For example, if you have a differential equation of this nature, we expect that if a certain expression is a solution to that differential equation, then that solution will be given in terms of y is equal to, and you have some expression here. So if the differential equation is a dy, then the solution will be expressions of y. So here, for example, you have dy squared and so on. So expect solutions to this differential equation to be expressions of y. Now, for an expression to be a solution to a differential equation, it implies that when you substitute it in the expression, it should be able to satisfy the differential equation given. For example, here with this expression, if something is a solution, it should follow that when you substitute, first, if let's say you have y is equals to some expression, get y, differentiate it, and place it there. Will it satisfy this expression? If it does satisfy the expression, then the expression you were given can be taken as a solution to the differential equation. I hope that part is okay. Any questions up to that point? Okay, let's find an example to just make sure we understand this kind of problem or what we're just explaining. Take this problem, for example, where we're given a differential equation, this, and we want to find if this expression is a solution to the differential equation. So how do we do that? To do that, you need to substitute. Where there's y, we're going to put that expression. Where there is the second derivative, we need to substitute the second derivative. And what we want to see is, will the left-hand side be equal to the right-hand side? The right-hand side is just 0. But would the left-hand side also reduce to 0? So let's see. First, we want to get dy dx, the first derivative of y. Since y is a constant c1 sine 2x, a constant c2 plus, of course, there, then cos 2x. When you differentiate, first differentiate the argument, which is 2x, the derivative will be 2. c1 remains, the derivative of sine will be cosine 2x. When you differentiate the second term there, derivative of the argument of that 2x will be 2. The 2 comes here. C2, the derivative of course will be negative, making the sign between to be negative, and then sine 2x. That's the first derivative. Now we get the second derivative with respect to x. When you differentiate the first term here, the derivative of the argument, that's a 2. This becomes 4. The derivative of course becomes negative sine. For the second part there, derivative of the argument will be a 2, making this a 4. Then when you differentiate the sign, we'll get cos 2x. After obtaining the expression for the second derivative, we're now going to substitute in that expression. Let's get the left-hand side. On the left-hand side, we have the second derivative, which is minus 4 c1 sine 2x minus 4 c2 cos 2x. All this is just the second derivative. To the second derivative, we need to add 4y. So we have 4. What is y? Y, remember, y is c1 sine 2x. Then we have plus c2 cos 2x. So we have this. So in this case, what do we end up having? So we have minus 4 c1 sine 2x minus 4 c2 cos 2x. This becomes plus 4 c1 sine 2x plus, this is a plus between, 4 c2 cos 2x. And what do we see? Negative 4 c1 sine 2x and positive 4 c1 sine 2x will give us 0. In the same way, this and this will also subtract to give us 0, implying that this will be equals to 0. So in doing this, we have shown that that expression is indeed a solution to the differential equation. So for an expression to be a solution, when you substitute it in the equation and its derivatives in the equation, the left-hand side should be equal to the right-hand side. Any questions on that before we move on to how to solve these differential equations? Okay, so the first one we'll start with is going to be first order differential equations. How do you solve first order differential equations? There are several methods that you can use, but the first method that we need to understand, and this is the most basic method, this is going to be separation of variables. So this is the most basic way of solving differential equations. Now, in separation of variables, the goal is always to separate. If you have an equal sign here, you want everything that has dy to be on the left side and everything that has dx to be on the other side. What do I mean? You want to make sure if you have a differential equation, let's say dy is equals dy dx, let's have something basic here. Let's have, what can I put here? X, y, maybe plus, maybe y squared. Y squared might be tricky. Let's say y sine x. You see that here you have a combination. You have a dy here, you have a dx there. So you want to separate the variables. Everything which has x should be on one side. Everything which has x should be on the other side. So here I'll keep dy on the left side. So I'll cross multiply the dx so that it goes on the right side. So it will have to multiply these two terms. Now, what else? I've separated the dy and the dx, but I'm still seeing there's a y attached to the dx. To separate completely, we don't want to have a y remaining this side. I want to get rid of this y so that it joins the dy. So you need to factor out that y. So now you have the y here, x plus sine x dx. And then to get rid of it from the right-hand side, now you have 1 over y dy on the left side, and then you have x plus sine x on the right side. So here you have separated these variables. The goal is that if you can separate these variables so that you have a dx and all the variables for x on one side, and then you have a dy and all the variables for dy on the other side, then it becomes possible for you to just directly integrate. You can now integrate the left side with respect to y and integrate the right side with respect to x, and this actually works out. Once you integrate, make y the subject of the formula and you're okay. For example, for this question, if you tried to use that approach, when you integrate the left side, this is 1 over y. The integral of 1 over y will be ln y. When you go to the right side, you have x there. When you integrate x, you get x squared over 2. When you integrate sine, you get negative cos. So this will be minus and the cos here. So this becomes the expression that you get. And then finally, because you have a ln involved here, you're going to have a constant in play here as well, so plus some constant. Mostly when you have to deal with the ln, you find that you might prefer to have this constant in form of a ln as well, so that you can say maybe this is a ln c. We'll see such expressions later on. Since you only want y, not ln y, you can get e on either side. So this will be the anti-ln will leave us with just y on the left side. On the right side, we'll have e to the power. The first part will be x squared over 2 minus cos x, then plus ln of c. So now we'll view it as if you are adding these two. And recall, if you're multiplying a to the power, let's say, x times b to the power y, not b, a to the power y, this is the same as just a to the power x plus y. When you're multiplying the same base, you just add the powers. So since we're able to view it as if these powers are just being added, then we can say that maybe what we had was e to the power x squared over 2 minus cos x multiplying e to the power ln of c. And ln of c, e to the ln of c, again, the anti-ln and ln, we know they will cancel out. So that now we have y is equals to c e to the x squared over 2 minus, of course, x. So this becomes the expression that will be our solution. Any questions there? This was just to demonstrate separation of variables. Now we're going to have more examples. We'll get a few from the tutorial sheet to just make sure you're comfortable separating these variables. You need to understand exactly how it happens. Sometimes you need to use a trick here and there, but the method is always the same. Take the first question. Okay, let's see one that looks more straightforward. First question does satisfy that condition. dy dx is equal to x to the power 3 sec squared y over 1 plus x squared. These methods will require you to remember how to integrate. Your ability to integrate here will really be tested. dy is equals to x squared 1 plus y squared to the power 3 over 2 altogether dx. And then we can look at even all of them if anything. Let's get c as well. 1 over e to the cos of x dy plus y squared sine x dx. So separation of variables, sometimes you need to force things. By force things, you need to add an in-between step for separation of variables to actually work. Let's see if these they'll be separable just the way they are. So the first step is being able to separate. Isolate dx with everything x, isolate dy with everything y. So can we do that? Observe that here I can write this as dy dx equal to, now I can view this as x to the power 3 over 1 plus x squared. Everything here has an x, and this is multiplying sec squared y. Everything here has y. So I need to get rid of everything y from the right side. The dx will cross multiply. So now I have dy is equal to x to the power 3 over 1 plus x squared. And then from here, now I have sec squared y dx. I'll divide both sides by sec squared y so that I get rid of that sec squared y from the right side. Now I have 1 over sec squared y dy equal to x to the power 3 over 1 plus x to the power 2 dx. Notice that now we have successfully separated these variables. Now the question is, do you know how to integrate sec squared y? And do you know how to integrate this? So this is what I meant when I said your ability to integrate will be tested. So before I remind you, how would you integrate on the left side? Anyone?
We use U substitution.
U substitution. U substitution. U substitution. What would be your U?
Like we try to do this.
This would be very tricky. There are easier ways. There are easier ways of doing it. Think through it. What's the first thing that comes to your mind? Let's have ideas.
So,
Yeah?
but if we try to use trigonometry,
Yeah, definitely we'll have to use
trigonometry,
trig. What's the first thing you want to use from trig?
like the identity for sec squared,
What identity?
that is a tan.
No, we'll not go that way. This is the first thing that should come to your mind. Yeah?
1 over 6. equal to cos squared y.
It is. That's the first thing that you need there. This is the same as cos squared y. It even looks better this way. Now, it is correct. That's the first thing. You see, now all you have to worry about is how to integrate cos squared. How do you integrate cos squared?
Can't we just use that identity cos squared to equal to 1, 1 minus sin squared?
Cos squared y is 1 plus, not minus. The one for minus is sine. Cos squared plus 1 plus cos 2y over 2. So this is basically 1 over 2 plus cos squared y over 2. So if you have to integrate this now, what did you get? The first part, the integral of half there, 1 over 2, 1. Integral cos 2y there. First, differentiate the argument, which gives you a 2 outside. 2 over 2. Of course, you have to divide, so it will be over 4. And then the integral of cos will be sine. So we get this. Are we okay there? Is that okay? Okay, so we now have 4y plus 1/4 sine 2y. This is just from the left-hand side. Now we do the same thing on the right-hand side. Integrate. This is over 1 plus x squared dx. Again, how do you integrate that right-hand side? How did?
Substitution.
What will be your u?
I don't know, maybe x to the power 3.
When you use u substitution, the odd variable should disappear. Let's try. If u is x to the power 3, du will be equals to 3x squared dx. So that dx will be 1 over 3x squared. So let's see. When you substitute this time around, you get u where is x to the power 3 over. You still have this 1 plus x squared. That is dx. You're putting 1 over 3x squared du. See that you've got no way of getting rid of this. You've got no way of getting rid of this. This is not working. Have you seen that?
Yes.
Okay. So your substitution here would not help us. So what can work then? ODEs really depend on your ability to integrate. Anyone to try? Which trig substitution here can work? How about we let, so remember how you integrate over s squared plus x squared without the square root. What substitution do we use in this case? Let x be equal to what? A tan. Do you remember? So for this problem that we have, a is 1. So we're letting x to be equals to 1 tan theta. So that dx will be equals to the derivative of tan is sec squared theta. So that now when we substitute, we're going to have, where there's x, we're putting tan theta. So we have tan to the power 3 theta over 1 plus tan squared theta. And then where we have dx here, we're putting the derivative, which is sec squared theta d theta. But remember the identity. 1 plus tan squared theta is the same as sec squared, meaning this and this are the same, leaving us with only integral of tan of theta d theta. So now the question has reduced to something that looks simpler, I feel. How do you integrate tan to the power 3 theta? You guys have forgotten your integration. So to integrate, just as you guys pointed out, you're going to separate this. Tan to the power 3 so that you present it as tan theta multiplying tan squared theta. Then you have to recall this identity. So make tan squared subject so that you have sec squared theta minus 1. And then substitute that. So this would be tan theta multiplied to the sec squared theta minus 1 d theta. At this point, you can distribute the tan so that you view this now as the integral of, you can distribute here or you can choose your u. U substitution now at this point can actually work. So you can choose your u, but just let's distribute first. So distribute the tan, you have tan theta sec squared theta minus tan theta d theta. Then distribute the d theta in the integral. So you have the integral of tan theta sec theta d theta minus the integral of tan theta d theta. So this is where you get to now integrate it. So doing the u substitution here, you'd have run into some problems. Just distribute, bring it to this point. Now this can be worked out using a u substitution. You will have to choose your u as tan, because when you differentiate u, you get sec squared, so that your d theta will be equals to du over sec squared theta. When you substitute this first part, will now be the integral of u sec squared theta, where there's d theta, you have du over sec squared theta. The sec squared and that will cancel, leaving you with only the integral of u du. This will be 1 over u, not 1 over u, 1 over 2 u squared. That's just for the first part. The second part is the integral of tan. what will be the integral of tan? Oh, this one we can actually proceed a little bit. Since we said u was tan theta, so this would be tan squared theta over 2. So now we have the integral of tan. The integral of tan, if you don't have it memorized, you can remember that tan is what? Sine theta over cos theta d theta. And then integrate this the way it is. You should be able to see that when you integrate this, the integral of this will reduce to negative ln of cos x, basically negative ln of cos x. So that will be the integral of sine over cos. So if you haven't mastered this, you can still go ahead and look at it the more standard way, as in doing it like that. So meaning that altogether, our expression reduces to minus that integral reduced to negative ln of cos. So that now this and this will make a plus. So here we'll have plus ln of cos x. In some cases, you find that instead of using negative ln of cos, you find that they'll give it as positive ln of, and then this will be sec. Some cases, this is what you have. These two expressions are the same. So that becomes the integral for the right-hand side. But remember, we're not dealing, this is, but there's not x, this is theta, we're working with theta here. We're not working with theta. Theta was what we ended up with after substituting. We now need to get rid of theta and go back to the original variable, x. So our relation was that x is equals to 1 tan theta. So where we have tan theta, it's just the same as just x. So on the right-hand side, where we have tan squared theta over 2, this is the same as x squared over 2. But now we have a problem. How about cos? So to get cos, we can take advantage of tan. If I make tan theta subject, I'll have x over 1. So tan is opposite over adjacent. So if my theta is here, tan is opposite, which is x, over adjacent, which is 1, implying that the longest side is x squared plus 1. Meaning that cos theta is equals to adjacent 1 over root of 1 plus x squared. So our expression for the right-hand side is equal to x squared over 2 plus ln of 1 over root of 1 plus x squared. Now I see that there's no way this expression will ever be negative, so I can just present it as this. Ln of 1 over root of 1 plus x squared. Putting them all together, the left-hand side, we concluded that it gave us, what was that? The left-hand side, we had, I bypassed it already. The left-hand side, we concluded that it gave us this. So combining them, this is the left-hand side, this is the right-hand side. This is the overall solution. Any question? Okay, so for the other questions, what we'll do is we'll separate the variables and we'll see if you guys can complete to solve and find the solution. So take dy is equal to x squared 1 plus y squared to the power 3 over 2 dx. And then the other we have, that's 1 over e, then we have cos x dy, it's y squared plus sin x, yes, is equals to 0. And finally, dx dy is equal to x squared y minus y over 2 y squared plus 4. Let's see if we can separate the variables for these expressions and let you solve them from there so that you practice your integration. So let's get the first one. For the first one, it looks a little bit easy. As long as this power does not affect the x, this is straightforward. Since that is the case, the power here is only for this part. So I can divide both sides by that part. 1 plus y squared to the power 3 over 2. Even this side will do the same thing. We're choosing this because it's everything which has y. That will leave 1 plus y squared